morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about one of the important topic in electromagnetic waves and their transmission lines as oblique incidence with parallel polarization. Right? So, before going to learn about this, the mathematical equation, derivation part, and related to this oblique incidence with parallel polarization, firstly, how many types of incidences occur? Then, depending upon that, oblique incidence with parallel polarization, we are going to learn in this particular lecture. Okay, then, so basically, incidences occur in two different cases. One is normal incidence and another is oblique incidence. Then normal incidence at a plane dielectric boundary and normal incidence at a plane conducting boundary we have discussed. So normal incidence at a plane dielectric and conducting boundary case, we have derived the tau and gamma. These are the two coefficients. The first one is called, tau is called as transmission coefficient and gamma is called as the reflection coefficient. So these two ratios are derived from the tangential components of both the electric as well as the magnetic fields. Right? So before going to derive the parallel polarization, transmission coefficient and the reflection coefficient, firstly, how the oblique incidence occur in this case. So the oblique incidence at a plane dielectric boundary also we have discussed. In that case, we learned about Snell's law of reflection and Snell's law of refraction. Then in that, we are going to learn one of the concept called total internal reflection. And based upon this, we have also learnt about this theta c. Theta is the notation for angle and c stands for critical angle. The critical angle is the angle at which the total internal reflection takes place is called as critical angle. And this and all already we have learnt in the previous lectures, that is oblique incidence at a plane dielectric boundary. Okay. Now here the oblique incidence means the total internal reflection and the measurement of critical angle is independent of the type of the polarizations. So this in this case, if the electric field is perpendicular to that plane of incidence and if the electric field is parallel to that of plane of incidence case, we have considered two types of polarizations. One is perpendicular polarization. It is also called as horizontal polarization. Now in this particular lecture, we are going to learn about the second type of polarization called parallel polarization, and it is also called as vertical polarization. Right? So in the perpendicular polarization case, we have derived the tau perpendicular and gamma perpendicular. Reflection coefficient and the transmission coefficient of perpendicular polarization we have derived. Now coming to this case, parallel polarization means mathematically we are going to derive the equations tau parallel and gamma parallel. Means reflection and transmission coefficients of parallel polarizations are denoted with tau parallel as well as gamma parallel. Okay. Now in order to write the mathematical equations for this transmission coefficient and reflection coefficient, firstly, how the electric field is parallel or perpendicular to that plane of incidence, depending upon that, how the waves are called as. Means, in the previous lecture, we have derived the tau perpendicular and gamma perpendicular, nothing but transmission and reflection coefficient of perpendicular polarization, where we have assumed the electric field is perpendicular to that of plane of incidence case, then those waves are said to be TE waves, transverse electric waves. Now here, if the electric field is perpendicular to the plane of incidence and the magnetic field is parallel to the plane of incidence case, those waves are said to be TE waves, transverse electric waves. And the magnetic field is perpendicular to the plane of incidence and the electric field is parallel to the plane of incidence case, waves are said to be TM waves, means transverse magnetic waves, right? So, here two cases we have discussed. In the previous case, we have discussed the TE waves, means the type of polarization is called as perpendicular polarization. It is also said to be horizontal polarization. Now, in this particular lecture, the magnetic field is perpendicular to the plane of incidence and the electric field is parallel to the plane of incidence case. The fields are configured as in the transverse magnetic modes. TM stands for transverse magnetic, where TE gives us transverse electric. Okay, transverse electric waves or comes under perpendicular polarization, whereas TM waves or modes are described in the parallel polarization. Now, consider that in order to derive these two coefficients, firstly, consider that a uniform plane wave is incident obliquely with E parallel to the plane of incidence. With E is parallel to the plane of incidence means magnetic field is perpendicular to that of plane of incidence. Hence, the waves are said to be here transverse magnetic waves or modes called transverse magnetic modes. Simply, we'll call it as TM modes. Okay, then coming to the analysis. Consider a planar interface between two dielectric media. Means in order to analyze this polarization, we need to consider one interface which is located at z is equal to 0 and below z equal to 0 and above z equal to 0. Means below z is equal to 0, we have medium 1 and above z equal to 0, we have medium 2. In the medium 1, characteristic parameters are epsilon 1 and mu 1, and for medium 2, those two are represented by epsilon 2 and mu 2. And sigma is equal to 0 for the both the cases. Why? Because in the medium 1 and medium 2, we have assumed as perfect dielectric medium. As we know that for a perfect dielectric medium, its conductivity sigma equal to 0. Hence, sigma, the one of the constitutive parameter for the dielectric medium, as sigma is equal to 0 for both the mediums. Okay. Then, a planar interface between two dielectric media, then a plane wave is incident at an angle from the median 1, means when the incident wave strikes the boundary with a making angle as theta I and part of it is reflected back to the same, then the angle is given by here theta R, means part of this is transmitted to the next medium, hence it is ET, this is EI, and here it will be ER. Okay, depending upon this, the plane of incidence contains the propagation vector and is perpendicular to the interface plane and to the phase of the wave. Okay, planes of the wave. Then there are two elementary orientations. Orientation of electric field is nothing but polarization for the electromagnetic waves, right? So those two are vertical as well as the horizontal polarizations. Okay, so there are two elementary orientations or polarizations for the electromagnetic fields. One is perpendicular polarization or horizontal polarization, and second one is parallel polarization or vertical polarization. Okay, now perpendicular polarization. The electric field is perpendicular to the plane of incidence and the magnetic field is parallel to the plane of incidence, and the fields are configured as in the transverse electric modes. Okay, so this already we have discussed in the previous lecture. And parallel polarization. So parallel polarization case, electric field is parallel to the plane of incidence and the magnetic field is perpendicular to the plane of incidence. And the fields are configured as in the transverse magnetic modes. Right? So under perpendicular polarization, we are going to learn about TE modes. Under parallel or vertical parallel polarization case, we are going to learn about transverse magnetic modes or TM waves. Okay, so the fundamental difference between these two, perpendicular polarization case, electric field is perpendicular to the plane of incidence and the magnetic field is parallel to the plane of incidence. Now coming to the parallel polarization case, that is completely reverse. Means the magnetic field is perpendicular to the plane of incidence and the electric field is parallel to the plane of incidence. Right? Next, any plane wave with general field orientation can be obtained by superposition of two waves with perpendicular and parallel polarizations. Right? Two concepts we are supposed to consider: perpendicular direction along with the parallel one. Okay? So, next, here is the diagram to analyze this parallel polarization. So, let me first introduce this one as incident wave is strikes the boundary. Part of this is reflected to the same medium and part of that is transmitted to the next medium. Means above this z is equal to 0, interface is exist as this one, and in medium 1, if you observe, both the waves are exist. One is incident wave and the another one is reflected wave. And in the medium 2, we have only transmitted wave, right? Where EI and HI are the two field strengths of electric as well as magnetic fields. And ER and HR are to be two field strengths of electric as well as magnetic fields. And ET and HT be the transmitted wave, electric as well as magnetic fields strengths, right? So if you observe parallel polarization means the electric field is parallel to the tough plane of incidence. That we need to remember clearly. And if you observe the directions of this incident wave and the reflected wave, 2R will be opposite to that of each. See, if you observe the incident wave strikes the towards the interface and the reflected wave is away to that of this direction. And if you observe, the incident wave direction and the transmitted wave direction will be similar, right? So ET, and if you observe this one as ER. And the making angles of both the three waves are representing theta I, theta R and theta T. Where beta I gives us here phase angle or phase constant representation for the incident wave and reflected wave as well as transmitted wave. And in order to analyze this parallel polarization, as we have considered in the case of perpendicular polarization, here also the plane we are going to consider is XZ plane only. Okay, so if you're considering XZ plane means the direction in which the wave is to be propagating is Y direction. Okay, so in this case also we are going to consider three cases of propagation vectors for incident, reflected and transmitted. Based upon that, we are going to derive the reflection as well as transmission coefficients. Okay, so in the previous case, how we have evaluated, here also this can be considered as XZ plane and direction of this will be consumed as like this. And gamma, if you are assuming the propagation constant for this is gamma and I stands for incident wave and the real axis component is given by here gamma 1 cos theta I and gamma 1 sin theta I. Always we used to consider the cosine function on the real axis and sine function on the imaginary axis. Why? Because as we know that it is depends upon the even and odd functions. As we know that cos of minus theta gives us cos theta only, whereas sine of minus theta gives us minus of sine theta, where this negative sign resembles the direction in which it is opposite to the other one. Right? The propagation direction is opposite to that. The previous one resembles the negative sign. Okay? So depending upon this, the propagation vector can be written as for the electric field strength and the magnetic field strengths for incident, reflected and the transmitted wave, where incident and transmitted waves are to be considered first quadrant of XZ plane only, whereas if you consider for the reflection, it will be second quadrant of XZ plane. Means the real term becomes negative and the imaginary term. XZ plane mean second quadrant of XZ plane means here the imaginary axis is lies along the negative axis and real term is lies along the negative axis, whereas imaginary on the positive axis only. Depending upon that, we are going to write electric as well as magnetic field strengths of incident wave, reflected wave, and transmitted waves. Okay, now to write that here, the electric field vector lies in the xz plane. Just now we have discussed xz plane. We are considering xz plane means y equal to 0 plane. We have to consider here y equal to 0 plane means the propagation vector is moving along that y direction component. Since the magnetic field is transversal to the plane of incidence, such waves are also called as transverse magnetic waves, and the mode of operation will be given by here TM mode, transverse magnetic mode. Now consider H vector, which will have only y component. Why? Because we have considered here the plane is xz plane. Okay. Now to write that this one, magnetic field intensity vector and electric field intensity vector for the incident wave. So as we have considered in the previous case propagation vector, this one, based upon this we are going to write the vector form, means the magnetic field intensity vector Hi is given by Ei by eta 1. Why we have got the magnitude term as Ei by eta 1. In general, we are going to write this one as Hi is equal to, along with its magnitude as Hi and the phase function e power minus gamma 1 into z. Right? I stands for incident wave and gamma 1 is the propagation vector for the medium 1 and z is the propagation direction. See here, gamma 1 into z means the medium 1, incident wave is aligned in the medium 1, hence we are representing the propagation vector as gamma 1. So Hi equal to, and in general intrinsic impedance eta is given by, it is the ratio of electric field strength E to the magnetic field strength H. Right? So in place of this Hi, if you are writing Hi is equal to, from this relation H is equal to E by eta. Right? So that's why Ei for incident wave, that is Ei by eta 1 into e power minus gamma 1 into, see how we have written that as gamma 1 can be written as gamma 1 cos theta I az plus gamma 1 sin theta I ax. Why? Because we have considered xz plane and the direction here y direction. Okay. So gamma 1 cos theta az plus gamma 1 sin theta I ax into z direction. Z component means z az plus x ax. If we multiply these two, we are going to get its value as gamma 1 cos theta I plus gamma 1 sin theta I. Gamma 1 into z cos theta I plus gamma 1 into x sin theta I is the value for the gamma 1 into z. Okay. The first one is for gamma 1 propagation vector for the incident wave, and this is given by z. If you multiply these two, then gamma 1 into z becomes gamma 1 cos z cos theta I plus x sin theta I into ay. And if you take here gamma 1 as common, then gamma 1 incident wave dot z is equal to gamma 1, if you take common, z cos theta I plus x sin theta I into the vector direction is ay. So Hi is equal to Ei by eta 1 e power minus gamma 1 into z cos theta I plus x sin theta I into ay. Now from this, now to write, so from the propagation vector we have got the magnetic field intensity vector as Hi. To derive Ei, electric field intensity vector for incident wave Hi, then it is given by, means that should be obtained from the one of the Maxwell's equation for the time varying fields. So as we know that for a time varying fields, to write the equation for Ei, we use here del cross Hi is equal to J plus JD. So what is this del cross Hi is equal to J plus JD? Means this is the equation, that is Ampere's circuit law, modified form of the Ampere's circuit law in the presence of displacement, current, density. So that is given by here del cross Hi, means this is the equation which is to be obtained from Ampere's law. Right? So this Ampere's law gives us, including with the displacement current density, that is del cross Hi equal to J plus Jd, where J is said to be conduction current density and Jd is given by displacement current density. Since J is equal to 0, why J 0? Means according to the conduction, means as we know that for a dielectric medium J equal to sigma into E, if you substitute this for a dielectric medium sigma equal to 0, then J becomes 0, right? So since J is equal to 0, this becomes del cross Hi equal to Jd only. So this Jd is given as dou d by dou t, means displacement current density, this is Jd, can be written as dou d by dou t. So d is a here vector. Okay. Now for a time varying fields, this changing with the time partial derivative term is replaced by j omega into d bar. Okay. So since for a time varying fields dou by dou t is replaced by j omega and j omega into d bar is to be substituted, then which is equal to j omega epsilon into E bar. Why? Because electric flux density D and electric field intensity E are related as D equal to epsilon into E. Okay, where D is a vector, E is also a vector. Okay, so now from that, if you write in place of del cross Hi by j omega epsilon 1 into Ai. Epsilon 1 is for medium 1. Why? Because we are writing incident wave field strength, where incident wave is exist in medium 1. That's why the permittivity is also replaced by here epsilon 1. Okay, then del cross Hi equal to j omega epsilon 1 Ei. Right? So from this Ei equal to, why? Because we are writing the equation for Ei. Now Ei equal to del cross Hi by this j omega epsilon 1. Right? So Ei equal to del cross Hi by j omega epsilon 1. Right? Now from this, expand this del cross Hi according to this, then Ei equal to minus 1 by j omega epsilon can be treated to a constant, and Ax means if we are writing determinant form for this, for the first row we are considering all the unit vectors as Ax, Ay and Az, and dou by dou x, dou by dou y and dou by dou z. For partial derivatives are to be considered in the second row, and in the third row we are going to consider the magnitudes of three directions. So here in the Hy we will have only the propagation direction only in y direction, means we have only y direction component magnitude only, and the rest x component and z components are zeros, and we have only y component, means that is given by, in the previous equation what we have, Hi means Ei by eta 1 e power minus gamma 1 z cos theta I plus x sin theta I is the magnitude of that Hi. Okay, so in place of that y component we just substitute Ei by eta 1 e power minus gamma 1 z cos theta I plus x sin theta I. To simplify this equation, which is equal to minus 1 by j omega epsilon 1 1 by j omega epsilon 1, then Ax into, if you write Ax here, then first consider first row and first column, then determinant between these two gives us dou by dou y of 0 becomes 0 minus dou by dou z of Ei by eta 1 into e power minus gamma 1 z cos theta I plus x sin theta I. Okay, then minus Ay into, means first row, second column, if you consider the depth between first and third becomes dou by dou x of 0 minus dou by dou z of 0 gives us 0. Then plus Az into, means first row and third column, if you consider determinant between these two gives us dou by dou x of Ei by eta 1 e power minus gamma 1 into z cos theta I plus x sin theta I. Okay, minus dou by dou by of 0 becomes 0. Then which is equal to 1 by j omega epsilon 1, and if we take in between these two, ei by eta 1 also a common, and if you multiply this negative inside, right, first ei by j omega epsilon 1 into eta 1 into, so for the first dou by dou z of this function, dou by dou x of e power x first becomes e power x, that is e power minus gamma 1 into z cos theta I plus x sin theta I into, if you are differentiating this one with respect to the z, so e power minus this becomes, already negative is there and here also negative is there, then minus of minus becomes plus, then e power minus gamma 1 z means gamma 1 cos theta I into ax as the first case. Gamma 1 cos theta I into ax. Okay, then this becomes next plus az into dou by dou x of, again in this also ei by eta 1, if we take common, then ei by eta 1 here, then if you say differentiate this one, minus gamma 1 into z cos theta I plus x sin theta I into, differentiation of this one with respect to x means this becomes minus sin gamma 1 sin theta I into az is left out. Okay, then in between ei by j omega epsilon 1 eta 1, and if we take in between these two, gamma 1 is also common, then e power minus gamma 1 into z cos theta I plus x sin theta I, if you take as common, then remaining is here cos theta I ax minus sin theta I az. Okay, so this can be obtained, and which is equal to, as we know that intrinsic impedance, this one, since intrinsic impedance eta 1 is equal to j omega 1 epsilon 1 by gamma 1, right? So if you simplify this one, means if you replace this total thing by eta 1 and this eta 1 gets cancelled, remaining is left out with ei only, right? So that becomes here ei equal to ei into e power minus gamma 1 z, this total term, e power minus gamma 1 into z cos theta I plus x sin theta I into cos theta I ax minus sin theta I az. Okay, so this is the way we have got the electric field intensity vector for the incident wave, which is to be obtained from the time varying fields. One of the Maxwell's equation is obtained from the Ampere's circuit law. Okay, so from the propagation vector we have written first magnetic field intensity vector for the incident wave, and from the Maxwell's equation we have got ei, that is electric field intensity vector for the incident wave. Now second case we are going to write here as for the reflected wave, right? So how we have considered means the similar case how we have considered the xz planes, cz and x. If you write minus gamma 1 cos theta r, and here it will be gamma 1 sin theta r, where r stands for reflected wave and the propagation vector for the reflection as this, and the making angle is given by theta r. Okay, so according to the vector addition, if you are going to write the equation, then it becomes minus z gamma 1 cos theta r means minus gamma 1 cos theta r az plus gamma 1 sin theta r ax into z vector means zaz plus xax. If you simplify like that, here the equation for the HR means reflected wave magnetic field intensity has obtained ER by eta 1, means here there is no negative, this becomes plus only. So minus ER by eta 1 into e power minus gamma 1 minus z cos theta r plus x sine theta r into ay. Why? Because reflected and incident wave field strengths are moving in opposite directions. Right? So now, based upon this, ER by eta 1 e power minus gamma 1 minus z cos theta r plus x sine theta r into ay is obtained. Okay. Now from this, in order to write ER means electric field intensity vector for the reflected wave ER, then how we have evaluated that one means according to the Ampere circuit law for the time varying fields, one of the Maxwell's equation upon expanding determinant form. Now we are going to have here the reflected wave field strength ER equal to ER into e power minus gamma 1 minus z cos theta r plus x sine theta r into cos theta r ax plus sine theta r az. Right? In the next case, and ht equal to, for the transmitted wave field strength ht and et can be written as here ht equal to et by eta 2. Why? Because now to write this one, transmitted wave electric as well as magnetic field strengths, the same equations how we have considered for the incident wave, and except in that what is the change is gamma 1s are replaced by gamma 2 and eta 1 is replaced by eta 2. Angles are also theta I are replaced by theta t. Why? Because the transmitted wave field strengths are existed in the medium 2. So ht equal to et by eta 2 e power minus gamma 2 into z cos theta t plus x sine theta t into ay. And for et means this is the equation for transmitted wave field strength for the electric field. So et equal to et into e power minus gamma 2 z cos theta t plus x sine theta t into cos theta t ax minus sine theta t az. Okay, this is the way first we are going to write from the propagation vectors incident, transmitted and reflected waves. We are going to have here 6 relations. Those are EI, HI, ER, HR and ET, HT. From all these 6 relations, we are going to derive the reflection coefficient and the transmission coefficient for the parallel polarization. Okay, then. So first we will tabulate all the 6 relations. So region is considered to be, means both the mediums are considered as a lossless medium. Right? So for a lossless medium, it is also called as perfect dielectric medium, means for sigma equal to 0. Means sigma equal to 0 case, propagation constant gamma can be written as gamma equal to under root of, according to the propagation characteristics, j omega mu into sigma plus j omega epsilon. If you take, then j omega mu into, if you substitute sigma by 0, then j omega epsilon, then inside the root, now j omega into root over mu epsilon. And in general, this gamma means propagation constant gamma constitute 2 relations as attenuation constant alpha and the phase constant as beta, which is equal to j omega root over mu epsilon. So if you compare both sides, real and imaginary terms, and the real term as alpha is equal to 0 and the imaginary term nothing but phase constant beta is given by omega root over mu epsilon. Okay, so alpha equal to 0, beta equal to omega root over mu epsilon. Now from all the past 6 equations, we just replace gamma 1 by j beta 1 and gamma 2 by j beta 2. Why? Because 1 and 2 resembles here medium 1 and 2 respectively. So EI is given by EI into e power minus j beta 1 z cos theta I plus x sin theta I into cos theta I ax minus sin theta I az. See, previously we have derived all these 6 equations, right? We are tabulating now all the 6 equations in a single format. And HI equal to EI by eta 1 e power minus j beta 1 into z cos theta I plus x sin theta I into AY. Similarly for HR and ER equations. HR is equal to minus ER by eta 1 e power minus j beta 1 minus z cos theta R plus x sin theta R into AY, and HR ER equal to ER into e power minus j beta 1 minus z cos theta R plus x sin theta R by cos theta R AX plus sin theta R AZ. Okay. See here there is no negative, all such positive only. ER by eta 1 and ET by eta 2. So for the region 2 we have transmitted wave, hence HT and ET are written as ET by eta 2 e power minus j beta 2 into z cos theta t plus sin theta t ay x sin theta t. Similarly for ET equal to ET e power minus j beta 2 into z cos theta t plus x sin theta t into, after differentiating this equation, is to be obtained as cos theta t ax minus sin theta t az. Right? So from the propagation vector we have 6 vectors as EI, HI, ER, HR and HT, ET. Now we are writing all the equations for the lossless medium. For the lossless medium, it is also said to be perfect dielectric medium. For that, gamma becomes beta only. Hence, we are replacing gamma 1 by j beta 1 and gamma 2 by j beta 2. Okay. So after finalizing all such equations, now we are going to derive the mathematical equation for the gamma parallel and tau parallel. Those two are transmission and the reflection coefficients for the parallel polarization or vertical polarization. Okay. So now the incident electric field intensity vector in the medium 1 means, first consider for the incident wave electric as well as magnetic field intensity vectors. From the table, EI equal to EHT, EI equal to HI equal to. Similarly, for the reflected electric as well as magnetic field strengths, ER by eta 1 into this equation and ER equal to this equation. Okay. Now, next one is for the transmitted wave field strengths. For the transmitted wave field strengths, electric and magnetic fields are given by HT equal to ET by eta 2 into e power minus gamma 2 z cos theta t plus x sin theta t into ay, and ET is obtained as like this. So consider all such 6 equations are like for EI as 1 and for HI is 2, for HR as 3 and ER as 4. Next, HT as 5 and ET as 6. Right? So after finalizing this 6 equations, now from the boundary conditions, why we are going to consider here boundary conditions means, now to analyze this one we have considered one interface, and below this interface we have medium 1 and above this we have medium 2. Right? So the boundary separating between two media means we must consider, now to write that reflection and transmission coefficients, we need to use the two boundary conditions between two dielectric media. Why? Because we are considering here two medium or both are dielectric medium only. Right? As we know that the boundary conditions for the two dielectric media in the electric fields as E1t equal to E2t. See, according to this statement, we can say that tangential components of both electric fields of both the medium 1 and 2 are continuous or across the boundary or interface. So we can consider this is the fundamental boundary condition between two dielectric media. Right? So from the boundary conditions, the tangential components of E and H must be continuous at the interface. Means at the interface means what is that condition? Z is equal to 0. So consider all the 6 equations. In that you just substitute Z equal to 0 in particular equations. Now first consider E1 equal to E2 equal to. So if you substitute in the previous equations, EI and ER equations means here if you consider EI equation, then substitute Z by 0. Then EI into e power minus gamma 1, this Z by 0 means we have only X component, that is X sin theta I into this total thing. And if you consider this ER, here also if you substitute Z by 0 and the ET equation also we substitute Z by 0. So from all the relations we have got EI plus ER into cos theta I plus ET into cos theta t. Right? See, both sides exponential functions are same, hence both gets cancelled. We have only this functions means EI and ER into cos theta I. Means, see here, if you observe, in the EI equation Z by 0, what is that? It is left out EI into e power minus gamma 1 X sin theta I x sin theta I into cos theta I ax minus sin theta I az. Right? This is for EI. And ER means if you consider this ER equation, ER equal to ER into e power minus gamma 1 x sin theta R into cos theta R into AX plus sin theta R into AZ. Okay. So if you compare both sides, this magnitudes of this one according to the boundary, these two are given by, means z components gets cancelled both sides. If you equate these two by adding, and both sides this gamma 1x sin theta I and sin theta R gets cancelled. Why? Because in order to derive the equations here, we are going to use Snell's law of reflection and Snell's law of refraction also. Now here we are using Snell's law of reflection, that is theta I equal to theta R. If you substitute theta I by theta R here, so these two gets cancelled, then this becomes like this. Okay. So similarly, if you replace like this, then by adding these two, one of the terms gets cancelled and other will be left over here as E1 equal to E2 equal to. So in the medium one we have incident wave and reflected waves, and in the medium 2 we have only transmitted wave. Based upon that, we have got EI plus ER into cos theta I equal to ET into cos theta T. Consider this as another equation, that is equation number 7. Okay, EI plus ER into cos theta I equal to ET into cos theta T. According to the Snell's law of reflection law, based upon the tangential components of electric fields of both the dielectric medium, and if you substitute at the interface z equal to 0, from all that we simplify the equations, EI plus ER into cos theta I equal to ET cos theta T has been obtained. And if you consider another relations, means for all the H equations, there also if you substitute z by 0. See, if you substitute z by 0 here, Hi in the Hi equation, z by 0. So Ei by, from this Hi can be written as Hi equal to Ei by eta 1 into e power minus gamma 1 x sin theta I. Okay. Now from this HR equal to ER by eta 1 into e power minus gamma 1 x sin theta R. Similarly for HT equal to ET by eta 2 e power minus gamma 2 x sin theta T. Okay. So by comparing these two, here also from all the relations 1 by eta 1. Why? Because this eta 1 is common for incident wave and reflected wave, and these two are existed in the medium 1 only. So 1 by eta 1 into EI minus ER equal to ET by eta 2. Okay. So in order to simplify these two equations, means reflection coefficient and transmission coefficients, we need to consider these two relations as first. See, now to simplify this one, transmission coefficient first. In both sides, if we equate with ET only from this equation, means from equation number 7, if we write for the equation for ET, then EI plus ER into cos theta I by cos theta T equal to ET. And from this equation number 7, if we write EI minus ER into, if you take this eta 2 into that side, eta 2 by eta 1 equal to ET. Right? So if you observe these two equations, RHS part is ET and ET only. If RHS part of these two are same, means LHS parts of these two are also same. Now simplify this equation, EI plus ER into cos theta I by cos theta T equal to EI minus ER into eta 2 by eta 1. So upon simplifying these two equations, means and consider these two as EI plus ER. So upon simplification, this becomes, if you take this term into this side, then it becomes eta 1 cos theta t, eta 2 cos theta I. So if you simplify this equation, now we are going to get here tau parallel, means transmission coefficient for the parallel polarization is nothing but Et by Ei equal to 2 eta 2 cos theta t by eta 2 cos theta t plus eta 1 cos theta I. Okay, so if you take this one into this side, then it becomes Ei plus Er into eta 1 cos theta I by eta 2 cos theta t equal to Ei minus Er. Okay, now if you simplify this equation, means Ei plus Er into eta 1 cos theta I equal to Ei minus Er into eta 2 cos theta t. So upon simplifying these two equations, we are going to get here the Et by Ei equal to 2 eta 2 cos theta t by eta 2 cos theta t plus eta 1 cos theta I. So this is the relation which is obtained, means for the transmission coefficient, and it is the ratio given by transmitted wave field strength to the incident wave field strength, and for the parallel polarization. So this parallel lines representing parallel polarization. Similarly for reflection coefficient, see for the reflection coefficient by adding these two, means previously what we have, the relation Ei plus Er equal into cos theta I by cos theta t equal to Et, and Ei minus Er into eta 2 by eta 1 equal to Et. So by adding these two equations, Ei plus Er into Ei plus Er into cos theta t by cos theta I equal to Ei minus Er into eta 1 by eta 2. Cos theta I by cos theta t, and here eta 2 by eta 1. This is I by t, eta 2 by eta 1. Now simplifying these two equations, we are going to get here this thing, gamma parallel, nothing but reflection coefficient, and it is the ratio which is given by reflected wave field strength to the incident wave field strength, and it is to be obtained as eta 2 cos theta t minus eta 1 cos theta I by eta 2 cos theta t plus eta 1 cos theta I. So the similar equations which we have got in the normal incidence at a plane dielectric boundary, their tau is given by 2 eta 2 by eta 1 plus eta 2, and here reflection coefficient gamma is given by eta 2 minus eta 1 by eta 1 plus eta 2. Okay, so like this, this is the case. Normal incidence means there is no refraction angle. Now here, along with the refraction means transmission, we have got tau parallel and gamma parallel as Et by Ei and Er by Ei. Okay, so this is the way we have got reflection coefficient and transmission coefficient for the parallel polarization. Now from these two relations, 9 and 10 equations, we have drawn one of the relation as 1 plus gamma parallel equal to tau parallel into cos theta t by cos theta I. To satisfy this one, first 1 plus gamma parallel means eta 2 cos theta t minus eta 1 cos theta I by eta 2 cos theta t plus eta 1 cos theta I. Okay, if you take LCM between these two, then eta 2 cos theta t plus eta 1 cos theta I by plus eta 2 cos theta t minus eta 1 cos theta I by eta 2 cos theta t plus eta 1 cos theta I. Okay, so if you simplify these two equations, means plus eta 1 cos theta I minus eta 1 cos theta I gets cancelled. 2 eta 2 cos theta t by eta 2 cos theta t plus eta 1 cos theta I. Okay, so if you observe this one, 1 plus gamma parallel equal to tau parallel into cos theta t by cos theta I. Okay, so in the previous case also, in the perpendicular polarization case also, 1 plus gamma perpendicular equal to tau perpendicular, we have derived one of the relation. Okay, so with this, what we have learnt in this particular lecture is, firstly, how many types of polarizations occurred. Depending upon that, we have analyzed parallel polarization. Now, to analyze this one, first we have considered three propagation vectors as for incident wave, reflected wave, and the transmitted wave. Now, from the propagation vectors, we have written all the six field intensities as electric field intensity and magnetic field intensity vectors for the incident wave, reflected wave, and transmitted wave. From that, we will consider for a lossless dielectric medium how the relations are to be obtained. Now, from that, tangential components of electric fields are continuous across the boundary, means from the boundary conditions. And if you use one of the Maxwell's equation for the time varying fields as Ampere's circuit law, and based upon all this, we have got tau parallel and gamma parallel, nothing but reflection coefficient and transmission coefficient for the parallel polarization or vertical polarization need to be evaluated. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.